The eyepiece presses cold against your face as Jupiter hangs above the roofline, and the red mark on its side looks like it is torn at the edge. Jupiter's great red spot is smaller, older, and far less settled than most people realize. If something is really peeling away from that storm, then the giant we thought we understood is telling a different story, and that story keeps getting stranger. Stay close to this channel for more deep space stories each week, and you will catch the clues before they turn into headlines. From Earth, the whole thing feels impossible. Jupiter is so large that NASA says you could fit about 1,000 Earths inside it if it were a hollow shell. Yet the part that grabs your eye is not the whole planet, but one bruised oval in a band of cloud, glowing red-orange like a wound that never closes. For generations, people treated that mark like a landmark, something old, familiar, and almost permanent. But now the edges no longer behave like a monument. They ripple, stretch, brighten, narrow, and at times seem to shed loose scraps into the surrounding air. And the deeper scientists look, from Hubble to Juno to Webb, the less this storm behaves like the simple picture in our heads. It begins as a famous spot in a telescope and ends as a problem that reaches from Jupiter's cloud tops to the future of planetary science. To see why this matters, we need to step back. Most people believe the Great Red Spot is a single, stable storm that has been slowly shrinking for a very long time, but otherwise remains basically the same. It is the old giant on Jupiter's face, fading a little, yet still understood. That belief sits quietly in the background of almost every picture we have ever seen of the planet. Jupiter does not have a hard ground the way Earth does. It is a vast world of hydrogen and helium, the same basic ingredients found in the Sun, but never packed tightly enough to ignite. Its clouds are made from ammonia, water, and other chemicals, layered like sheets of weather stacked over impossible depth. The planet spins once in about 9.9 hours, so fast that its atmosphere is combed into belts and bright zones by fierce jet streams. That speed matters. On Earth, mountains, forests, oceans, and continents interrupt the flow of air. On Jupiter, there is no solid surface to rough the wind up and slow it down, so storms can keep going for years, even centuries. Some winds near the equator can reach 335 miles per hour, and the whole planet feels less like weather on a world and more like weather becoming the world itself. The Great Red Spot sits in Jupiter's southern hemisphere. It is an anticyclone, which means a storm spinning around high pressure, the opposite spin direction of an Earth hurricane. For a long time it has been large enough to swallow Earth, though not nearly as large as it once seemed through older observations. Today it looks like a red eye, but that calm label hides something restless, muscular, and very alive. People have been staring at it for hundreds of years. Some records suggest a similar feature may have been seen as early as the 17th century, though scientists still debate whether that older spot is the same storm. By the late 19th century, observers were watching it more steadily, sketching it by hand night after night. It entered culture the way Saturn's rings did, as one of those pieces of the sky you feel you already know before you truly do. That familiarity is part of the trap. When something has been in astronomy books for generations, the mind starts to file it away as finished knowledge. The Great Red Spot became a logo for Jupiter, almost like the planet had been born with it. It was easy to forget that what looked fixed from far away might actually be changing every day, every hour, every minute. And there was another reason people relaxed around it. The storm lasted. That alone made it feel different from the temporary weather we know at home, where clouds split apart before lunch and thunder rolls away by evening. Compared with a summer storm above your house, Jupiter's red oval seemed less like weather and more like geography, like a continent made of wind. It was not just famous because it was big, but because it endured. Even its shrinking could be read the safe way. If a storm slowly narrows over decades, the easy story is that it is aging in place. Like an old spinning top losing a little energy, it still feels predictable. You imagine a long, graceful fade, not a sudden tear, not a hidden pulse, not a strange failure deep inside the machine. The mind prefers the smooth curve over the sharp surprise. NASA's long-running Outer Planet Atmospheres Legacy program, led by Amy Simon at Goddard Space Flight Center, helped give scientists their clearest year-by-year view of Jupiter. Those repeated observations mattered because giant planets reward patience. A single pretty image can mislead you. A slow movie, built over years, can reveal the rhythms underneath, the little changes that a human eye might otherwise dismiss as noise. By the time NASA's Juno spacecraft reached Jupiter on July 4, 2016, the old assumption still had force. Yes, the Great Red Spot had shrunk, Yes, its shape had changed, but most people still pictured the basic engine underneath as one deep, durable storm, staying where it had always stayed between the same jet streams. The top might wrinkle, but the core, we thought, remained the same old giant. That picture felt reasonable. Jupiter's belts and zones look like wide, painted lanes wrapping around the planet from horizon to horizon. The Great Red Spot sits trapped between strong streams to the north and south, almost like a leaf caught between two river currents. When you see that placement again and again in image after image, it looks secure. Not healthy, maybe, not growing, but secure. And security is a powerful illusion in space. A moon can seem like a dot until you realize it is bigger than Mercury. A planet can look still until you learn its clouds are racing faster than a rifle bullet. Jupiter does this to the mind all the time. It takes things too large to feel and makes them look ordinary from far away. So the prevailing belief held. The Great Red Spot was ancient. It was shrinking. It might one day settle into a smaller form. But it was still, at heart, one stable storm doing one stable thing in one stable place. That was the picture many viewers carried into the new decade, and it is the picture the next evidence would begin to crack. Then came the moments that did not fit. In 2019, images showed red material seeming to slough away from the Great Red Spot, as if flakes were peeling off the storm's edge. That looked less like a dignified old vortex and more like paint stripping from a wall in wet weather. What we had taken for granted was about to become much harder to defend. Right the instant your mental picture of Jupiter shifted into the comments below. That one detail helps this channel find the exact turning point where curiosity catches fire, and it shapes the next story we build together. At first, the flakes looked like bad news. If the storm was losing visible pieces, then maybe the whole thing was finally coming apart. That was the expectation, and it spread fast because it matched the shrinking story people already knew. A smaller storm shedding red scraps sounds like a candle guttering out. But when Philip Marcus at the University of California, Berkeley, and his colleagues studied the behavior, the simple death scene did not hold. Reporting around the American Physical Society's Division of Fluid Dynamics meeting in 2019 described a different possibility. The flakes, Marcus argued, could be surface-level weather, the result of the Great Red Spot merging with small anticyclones and deflecting a nearby cyclone. In other words, the top looked ragged, even if the deeper engine stayed strong. That was the first hard surprise in the modern version of this story. People expected a grand storm and collapse. Scientists instead saw signs of local turbulence around a storm that might still be structurally powerful. It was like seeing chips fly off a crashing wave and realizing the wave itself is still being driven by water far below the foam. The dramatic part was real, but the meaning of it was not obvious. Marcus used a useful image. He compared the visible cloud layers to the top tiers of a wedding cake. What telescopes catch most clearly is not always the full body of the system beneath. That matters on Jupiter, where the storm is not a flat stain, but a thick, layered tower of moving gas extending into deeper pressure. A torn frosting edge does not tell you the full strength of the cake. Soon after that, Juno added weight to the mystery. Scientists expected the Great Red Spot to be deep, but there were limits to how deep even bold guesses went. Then Juno's microwave radiometer and gravity measurements looked below the cloud tops. What they found was not a shallow swirl, but a storm with roots plunging hundreds of miles down. The familiar red oval turned out to be less like a scab on the atmosphere and more like the top of a buried pillar. In October 2021, Southwest Research Institute shared Juno results led by principal investigator Scott Bolton. The spacecraft had shown that some Jovian storms extend about 60 miles down, while the Great Red Spot itself reaches more than 200 miles beneath the visible clouds. Marzia Parisi of NASA's Jet Propulsion Laboratory, working from Juno flybys and gravity data, helped constrain the depth to about 300 miles, or roughly 500 kilometers. That is 50 to 100 times deeper than Earth's oceans. Again, the expected picture broke. If the Great Red Spot were just a decorated patch of upper cloud, then flaking edges might tell most of the story. Instead, the visible storm was only the top expression of something thick, heavy, and rooted. It was like noticing a ripple in a tablecloth and learning it is tied to a steel beam under the floor. The surface event stayed interesting, but it could no longer stand alone. Juno did more than measure depth. It also showed that Jupiter's belts and zones reach around 1,900 miles, about 3,000 kilometers, below the cloud tops. That means the Great Red Spot does not spin above a shallow painted sky. It lives inside a deep atmosphere where chemistry, pressure, heat, and motion are linked across enormous vertical distance. On Earth, weather is a layer. On Jupiter, weather is a cathedral. That changed how the flakes had to be read. A peeling edge might not signal simple loss. It might be an effect of stress between layers, or an interaction with nearby storms, or a response to currents pressing from the north and south. The storm was not a sticker coming loose from glass. It was more like a living knot in a river, tied to motions above it and below it at the same time. Then the story rose upward. If Juno showed that the Great Red Spot reaches down, the James Webb Space Telescope hinted that its influence may also reach higher than expected. Scientists had assumed the upper atmosphere above the storm might be fairly plain. That was the expectation because Jupiter receives only about 4% of the sunlight Earth gets, and the equatorial upper atmosphere was thought to be rather even, a quiet roof over a noisy house. Webb did not find a quiet roof. In release material dated June 25, 2024, scientists described dark arcs and bright spots above the Great Red Spot, features that had not been seen before in such detail. Henrik Malin of the University of Leicester said the team had expected the region to be boring and found the opposite. Their results, later published in Nature Astronomy, suggested that gravity waves might be shaping the upper atmosphere there. That means motion from deeper, turbulent layers may be climbing upward like ripples through stacked sheets. Once more, the expected picture failed. Scientists anticipated bland sky above the famous storm. They found texture, structure, and signs of energy transfer. It was like opening the attic above a loud room and discovering the ceiling itself is flexing with the music. The Great Red Spot was not just a stain on Jupiter's face. It was part of a whole vertical conversation. And then Hubble delivered the strangest twist yet. Between December 2023 and March 2024, the telescope watched the Great Red Spot over about 90 days, enough time to track one full oscillation cycle. Amy Simon and colleagues measured the storm's size, shape, brightness, color, and vorticity, which is a word for how strongly air is twisting. They were not just checking whether the spot looked pretty, they were checking whether it behaved consistently. It did not. Simon said the team expected slight changes in longitude, the storm's east-west position, but did not expect to see its size oscillate. The Great Red Spot was squeezing in and out while moving faster and slower, jiggling, in her words, like a bowl of gelatin. The cause, she said in NASA and ESA releases on October 9, 2024, had no hydrodynamic explanation, yet. That is scientist language for, we can describe it, but we cannot fully explain why it is happening. Think about how big that statement is. This was not an amateur telescope catching one odd frame through shaky air. This was Hubble, watching with the right cadence, collecting enough detail to turn the storm into a time-lapse. And the result was not a clean model, but a wobble. A planet-sized storm larger than Earth was behaving like something squeezed in a hand. Mike Wong at the University of California, Berkeley, offered a vivid picture. He said the Great Red Spot may be pushing against jet streams above and below it, like sandwich bread bulging around too much filling. That image matters because it gives a mechanical feeling to something otherwise abstract. You can imagine pressure from both sides, a storm too large for the lane it occupies. Not a calm old monument, but a body under strain. By now the story had a rhythm. People expected stability. Scientists found peeling, deep roots, upper atmosphere structure, and a 90-day squeeze. Each new clue pushed against the old assumption from a different direction. If this were just a storm slowly shrinking in place, the evidence should have become simpler over time. Instead, the closer we looked, the more connected and dynamic it became. And yet, right here, it is important to slow down. Even now, the people studying Jupiter do not all agree on one neat cause for every strange thing we see. The flakes can be modeled as weather interactions. The squeeze has no agreed hydrodynamic explanation. The upper atmospheric patterns may be shaped by gravity waves, but follow-up work still matters. This is not a solved puzzle with one final caption underneath. That hesitation is not weakness. It is the sound of science staying honest while the picture sharpens. When experts admit what they do not know, you can trust the parts they do know much more. And on Jupiter, what they know is already wild enough. The famous red oval is not passive. It is exchanging energy with its surroundings in ways that cut through layers of the atmosphere. Then another piece slid into place from a different direction. In July 2024, Yale announced results from a study led by Caleb Keaveney with Gary Lackman of North Carolina State University and Timothy Dowling of the University of Louisville. Using the EPIC model, they simulated how smaller passing storms affect the Great Red Spot. Their conclusion was both simple and startling. Small storms can feed it. That sounds modest until you feel what it means. The old expectation said the Great Red Spot is a lone giant, aging mostly on its own. The simulation suggested that nearby storms can strengthen it and modulate its size, almost like delivering fuel. Keaveney described it as feeding the Great Red Spot a diet of smaller storms. Suddenly, the red oval looked less like a fading relic and more like an organism in an ecosystem. That matters because it reframes shrinking too. If the storm depends in part on a steady diet, and that diet changes, then size is not just about old age, it is about supply. It is about interaction. It is about whether Jupiter's broader weather network is still delivering the right kind of disturbances at the right times. A starving storm tells a different story than a dying one. The Yale team connected this to something closer to home. On Earth, long-lived high-pressure systems called heat domes, or atmospheric blocks, can be sustained by interactions with smaller nearby weather features. So the Great Red Spot is not just a cosmic oddity. It may also be an exaggerated version of a familiar rule, one that reaches from a summer heat wave over your town to a storm on a planet 484 million miles from the Sun on average. That is the domestic and the cosmic touching fingertips. By this point, the phrase, "something broke off from Jupiter," starts to feel both true and too simple. Yes, observers saw pieces seeming to peel away. Yes, the edges looked unstable. But the deeper story is not that Jupiter casually lost a chunk. It is that one of the solar system's most famous structures is behaving like part of a living system, not an isolated scar. The visible break is the clue, not the whole event. And that is why scientists cannot give one clean answer yet, because Y on Jupiter is stacked. There is the visible Y, the cloud level Y, the deep structure Y, the jet stream Y, the upper atmosphere Y. A flake may come off for one immediate reason and still belong to a far bigger process underneath. On Jupiter, causes nest inside causes the way storms nest inside storms. By the end of this reveal, the Great Red Spot looks different. It is not just shrinking, it is pulsing, it is interacting. It may be fed by smaller storms, squeezed by neighboring jet streams, and connected to wave activity above and deep structure below. What looked like one old red mark now resembles a whole weather engine showing stress across many floors of the same building. And here is where this stops being about one storm and begins being about us. When a thing we thought was stable turns out to be active, layered, and partly unexplained, it forces us to ask how often we mistake familiarity for understanding. Pass this video to the one friend who thinks Jupiter is already a solved chapter in the textbook. That share matters because the fastest way to wake curiosity is to place a fresh mystery inside a familiar name. The deeper reason this story matters is not just that Jupiter is weird. It is that Jupiter is a giant laboratory for questions that reach far beyond one planet. How do storms survive without a solid surface beneath them? How does energy move up and down through an atmosphere? How much of what we see from far away is surface, and how much is structure? The red spot becomes a mirror for how science itself learns. There is also a practical future hiding inside this. Astronomers do not study Jupiter only to admire Jupiter.
Gas giants are common around other stars. If we want to understand distant worlds we can barely see, we need to learn how deep winds, chemistry, heat, and magnetic effects behave on the giant planet next door. Every surprise on Jupiter sharpens the way we read far dimmer planets in the dark beyond our solar system. So, Act 3 is not about a single answer arriving. It is about a new kind of watching. Now that scientists know the Great Red Spot can wobble over about 90 days, appear to shed material, and tie into deeper and higher layers than expected, future observations can be timed more carefully. The storm is no longer just something to photograph. It is something to track, like a heartbeat. That changes the value of patience. A backyard observer with a modest telescope may catch a brief colour shift. A professional team may compare that shift with ultraviolet data, microwave sounding, gravity measurements, or infrared structure. A child looking up from a driveway sees a bright planet. A research group sees a moving target with layers of cores still hidden in motion. The same dot in the sky now holds more jobs. The coming years matter because several missions stretch this story forward with real dates attached. NASA says Europa Clipper will travel about 1.8 billion miles or 2.9 billion kilometres and reach Jupiter in April 2030. It is designed for 49 close flybys of Europa, the icy moon that may hide a deep ocean. That mission is aimed at habitability, which means weather conditions there could support life. But it will still enter the same giant system shaped by Jupiter's atmosphere and magnetic environment. ESA's JUICE mission widens the horizon even more. According to ESA, JUICE launched on April 14, 2023, and is expected to arrive at Jupiter in July 2031. Its route includes an August 2024 lunar Earth flyby, an August 2025 Venus flyby, a September 2026 Earth flyby, and a January 2029 Earth flyby. That kind of itinerary feels almost absurdly patient, like mailing a question across the solar system and waiting years for the envelope to come back opened. Why bring up moon missions in a story about a storm? Because Jupiter is not a backdrop. It is the environment that shapes the whole neighborhood. Its radiation, gravity, magnetic field, and deep atmosphere create the stage on which those moons move. If the planet's weather engines transfer energy in ways we still do not fully map, that affects how we understand the broader system those spacecraft will enter. There is also a human lesson in the method. Notice what solved nothing and what solved something. One dramatic image solved nothing by itself. Repeated observation, better timing, and different instruments solved pieces. Hubble showed the 90-day squeeze. Juno measured depth down to roughly 300 miles below the cloud tops.
Webb exposed dark arcs and bright spots high above the Great Red Spot. The truth did not come from one heroic snapshot. It came from layers of attention. That applies at home more than people realize. When your weather app says a storm front is coming, that forecast is not magic. It is built from repeated measurements, not one glance out a window. Jupiter pushes that principle to an extreme. A storm larger than Earth can fool us if we only check in once. A storm that looks stable in a textbook can turn strange when observed with the right cadence over 90 days. And there are still blunt, open questions. Why exactly does the oscillation happen now in the way Hubble saw it between December 2023 and March 2024? How directly are the visible flakes tied to deeper changes rather than local edge events? How much do smaller storms feed the Great Red Spot in reality, not just in simulation? How do gravity waves above the storm connect to the deeper turbulence below? Each question is simple to say and difficult to close. The timeline ahead gives scientists a way to ask better. A future observer can compare Hubble-style imaging against older Opal records. They can test whether brightness peaks again when the storm reaches its widest point in an oscillation. They can look for repeated dark arcs above the storm in infrared. They can ask whether color changes at the top match deeper signals from radio or gravity studies. Jupiter is turning into a long-term experiment. That experiment also leans on people outside major observatories. The 2019 flaking episodes were noticed in part by amateur astronomers. That matters. The sky is too large and time is too continuous for a few teams alone. A person with patience, clear air, and a decent setup can spot a change that later becomes part of a professional campaign. Sometimes discovery begins not in a control room, but in a backyard with numb fingers and a thermos. By the time Europa Clipper arrives in April 2030, and by the time JUICE reaches Jupiter in July 2031, the Great Red Spot may not look exactly as it does now in today's mental image. Amy Simon's team suggested it may keep shrinking before stabilizing into a less elongated shape. But smaller does not mean simpler. A shorter, tighter storm could be more constrained by the jet streams around it, and therefore easier, in some ways, to diagnose. The old giant may become a sharper instrument. There is a quiet emotional shift in that. For years, people asked whether the Great Red Spot was disappearing. Now the better question is what kind of object it is becoming. Not a lost story exactly, more a transformation story. Like an old city changing street by street, the famous outline may contract while the deeper patterns become clearer. The change itself becomes the message. And if you ever step outside on a cold evening and see Jupiter above the trees, that dot becomes harder to dismiss. You are not looking at a ball with a painted feature. You are looking at a system where storms may be fed, squeezed, peeled, and echoed across layers we cannot even imagine standing inside. You are looking at a world where the word weather stretches until it almost breaks, and you are watching it in real time, across years that now have names, instruments, and dates attached to them. What comes next will not arrive with a drum roll. It will arrive as another night of data, another orbit, another image with one edge just slightly wrong. Somewhere, a researcher will line that image up against an older one and notice that the storm has tightened by a little more, brightened at one core, dimmed at another rim, or sent another strange signal into the air above it. The future of this story is not a single explosion. It is a sequence of quiet corrections. That is how tomorrow changes, not by replacing Jupiter, but by replacing our confidence about Jupiter. A storm we thought we recognized has already forced scientists to reopen basic questions about depth, feeding, oscillation, and energy flow. And because giant planets are so common in the galaxy, every corrected idea here travels outward. One better model of Jupiter becomes one better guess about worlds we may never see clearly enough to photograph. So here is the image to keep. A red oval on a striped planet. A span of 90 days between December 2023 and March 2024. A telescope watching a storm bigger than Earth squeeze in and out like gelatin. A spacecraft measuring routes roughly 300 miles deep. And above that same storm, dark arcs and bright spots hanging where scientists once expected almost nothing at all. Save this story somewhere private and come back to it the next time Jupiter rises bright in the evening sky. That small habit will train your eye to notice how fast science moves when the universe stops behaving the way the old picture said it should. Because the most exciting thing here is not that something seemed to break off from Jupiter. It is that the break exposed motion. It exposed depth. It exposed ignorance in the best possible sense, the kind that pulls the next mission forward and keeps the next observer awake a little longer. The future will not find Jupiter simpler. It will find us better at seeing how alive it has been all along.